All right, happy Monday. It's 9th week, and we have Thanksgiving this week also. So that's exciting. All right, let's. So this is where we left off on Friday. I talked about the Gibbs Sampler, and I said kind of the idea is you're going to take a multivariate thing and break it down into univariate probability distributions that are conditional on conditioned on the other variables. Okay, so for example, if you have a multivariate Gaussian, okay, you can condition it by locking in one of the variables, and that becomes a univariate Gaussian distribution. Right. So even if there's covariance, if you so if you have a joint distribution, if you lock in, say, y, then it becomes a univariate probability distribution on x. We can generalize this, and we'll get the Gibbs Sampler here. So let me just okay. This is week 9-1. Okay, so let me just kind of write a little bit about the Gibbs Sampler. All right, and the idea is, we have the big idea is there is a target multivariate PDF. Okay, so we'll call this P of the vector x. And this might be, maybe it's difficult to sample from directly. Okay, keep in mind x is a vector, kind of a multivariate vector. So something like x1, x2, x3, up to xd. Okay, and then we'll just say for the chain at time t, we're going to say x at time t is going to be x1 at time t, x2 at time t, x3 at time t, and xd at time t. Okay, and what we're going to do is to produce the next draw. Okay, that is x at time t plus 1, the vector x at time t plus 1, we will draw from the univariate conditional distributions. Okay, so what we're going to do is we're going to draw x1 at time t plus 1 will come from the probability distribution of x1 given that we have the values x2 at time t, x3 at time t, all the way up to xd at time t. Okay? Once we have drawn x1 at time t plus 1, then we move to the next value. We're going to do x2 at time t plus 1, and this is the conditional distribution of x2 given that x1 has value t plus 1, the value that we just drew. x3 is at time t, up through xd at time t. Okay, so this is the value that we just drew. Then the next value, x3 at time t plus 1, will come from the univariate probability distribution of x3, given that x1 has value t plus 1, x2 has value t plus 1, okay? And then we would have x4 at time t up through xd at time t, all right? And we would continue this so that anytime we're drawing x sub I at time t plus 1, it would come from the probability distribution of xi given x1 at time t plus 1, x2 at time t plus 1, okay, up through xi minus 1 at time t plus 1, and then xi plus 1 at time t plus at time t up through xd at time t. Okay, and this last line is pretty much the Gibbs sampler. That at any point in this draw, if you have, x as a vector of 20 dimensions, to draw the 12th value, okay, you would have already drawn the previous 11 values for the next iteration, and you would kind of lock those in. And then you haven't drawn the values 13 through 20, and so you use the most current value, which is from the older iteration. I know there's a lot of t's and t plus 1s, so I just want to kind of pause here just for a brief minute and just make sure everyone is okay with what we have said here. So the hard part is breaking everything down into univariate conditional distributions. And we can do this, relatively, for some well understood distributions, it's relatively easy to do. Like the bivariate normal, we would have to kind of break it apart into univariate conditional ones. But other ones, the breaking it apart into conditional distributions is a challenge, okay? So finding each of these conditional distributions can become tricky. All right. Okay, so this setup, however, works very well in what we call a hierarchical model. So I'm going to introduce the hierarchical model. There, I'm going to flip to the next slide. All right. Okay, so the Gibbs sampler works very well for hierarchical models, okay? And that's because hierarchical models are set up via conditional distributions. Okay, so kind of deriving a conditional distribution is not necessary. It's already been done. Okay. All right, so we are going to revisit the Bayesian baseball player example. Is that all right? Okay, so we revisit the Bayesian baseball player example. Okay, so when we first said it, okay, when we so we said each player has some unknown or has some kind of hidden batting average, right? Like each player has an inherent batting average that is what we treat as a random variable. Okay, each player has some random variable for their batting average. Okay, and here I'm going to just call this theta. Okay, I know earlier we called it P, but we're going to say theta is their batting average. And what we said is that we had a prior distribution. Okay, before we look at any of the data for the player, we said that our knowledge of baseball says that batting averages should be something between 0.2 and maybe 0.34 or something like that, right? And that, you know, it's unreasonable to conclude that a player has a batting average of 400 just because they got 4 out of 10 hits, okay? We also said there's a prior distribution representing prior distribution for theta. Okay. All right. And it's basically along the lines that batting averages are almost always, say, between 0.2 and 0.35. Okay. And so we said that. And to do this, we used the beta prior distribution, okay, to, I guess, model this. We used the beta distribution for the prior. Okay, we said we have a beta 81, 219 for the prior distribution of theta. Okay, so this is all review, and I just want to make sure that we all feel good about what I've written here, right? So this, I'm hoping, feels familiar, and this is where we kind of were a few weeks ago, right? We said this was the prior distribution for theta, and it was the beta distribution 81, 219. All right, and some of you might have had questions at the time and said, how did you get 81 and 219? I don't know if you guys had that question. And I just said, you know, I did some guess and check, and this is what I came up with, and it looked good, right? That's a fine answer, okay? But what we can do in a hierarchical model is we can say, you know what, I'm not ready to just hard commit to these numbers 81 and 219. Maybe I want a different number. Maybe I want to treat this number 81 as a random variable and this number 219 as a random variable, rather than just picking 81 and 219 via, you know, in a slightly arbitrary manner. We can then say these numbers 81 and 219 themselves are random variables. The values that go into my prior distribution, those those parameter values themselves can be treated as random variables. Is that okay? So we're going to complicate things, right? So in a hierarchical model, okay, we will not arbitrarily select values like 81 and 219 as parameters for the prior distribution. Okay. Instead, we will treat the shape parameters. Okay, so we have alpha equal to 81 and beta equal to 219. We will treat the shape parameters alpha and beta as random variables themselves. Okay, so that means the two shape parameters will come from some other distribution. Okay, so the two shape parameters for our beta distribution come from a random distribution. Our beta distribution prior. So the two shape parameters also come from a random distribution, okay? Now, when we do that, that random distribution may itself have parameters, right? Okay, so so let me just kind of draw kind of a diagram. All right, so our data consists of the actual observed data. What does it consist of for a baseball player? Like what am I recording in my notebook when I'm gathering data? Hit or miss, right? Hit or not a hit, okay? Observed data consists of zeros and ones, okay? For hits slash, I guess, outs, okay? All right, so we would have like 1, 0, 0, 1, 0, 1, or something like that, right? 0, 0. Okay, and so this is Bernoulli data, okay, for what happened at the plate. So this is our observed data, and we're going to say this, the data comes from a Bernoulli distribution, right? And the Bernoulli distribution is generating whether an at-bat was a hit or a miss, okay? The Bernoulli distribution, these values are treated as randomly drawn from the Bernoulli distribution. Bernoulli distribution is defined by the kind of player's batting average theta. Okay. And where is this theta where does the value theta come from? Okay, this comes from a beta distribution. With shape parameters alpha and beta. Okay, alpha. Okay, so earlier we had manually set alpha and beta, right? So earlier we kind of arbitrarily selected alpha equal to 81 and beta equal to 219, okay? But for a hierarchical model, these are drawn from a distribution. Okay, so alpha is going to come from, this is going to be known as the hyper prior. Okay, and beta also comes from either the same or a different hyper prior. All right, and then the hyper priors themselves, so can have parameters, okay? And those would be like hyper priors if you wanted, okay? And it can keep going and going and going, but most likely to avoid the problem of infinitely many hyper prior distributions, we are going to just select kind of a flat, uninformative prior, okay? Use an uninformative prior distribution. Okay, and the reason why we would want to do something like this is that we can now represent data for more than just one player, okay? So rather than just looking at one player, okay, we can say we're going to get a whole bunch of different theta values, okay? So let me kind of just draw this, right? So we've got some uninformative hyper prior distribution. This is just the name for the distribution from which the parameters of the prior distribution are drawn. Okay, so it's just, a hyper prior is just something above that. Okay, and so from this, we are going to draw the value alpha, shape parameter 1, and beta. Okay, and these two together make our beta distribution prior. Okay, and then from the beta distribution prior, we will draw theta 1. This will be player 1's batting average. Okay, and from this beta distribution, we'll also draw theta 2. This will be for player 2. And we'll also draw theta 3 for player 3, and so on and so forth. Okay, so for however many players you need, you'll just keep drawing. And from each of these things, so this theta 1 will create a Bernoulli distribution. And this will generate your data. 0, 1, 0, 0, 1, something like that, right? This theta 2 goes into a Bernoulli. What do we get? 1, 1, 0, 0, 0, okay? This gets a different Bernoulli. Zero, 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 1, okay? Something like that, all right? So on and so forth, right? So you get Bernoulli, and it's going to just produce kind of the actual hits or misses that we observe. Right? And so this would probably be arranged in some kind of matrix or something. Is that all right? Does this diagram make sense? Okay, so we're talking about multiple players, and each player is generating hits or misses, okay? But we're assuming that those hits or misses are not totally random, but they're determined by a random Bernoulli distribution with some unknown parameter value theta 1, which itself has been drawn from a beta distribution. And this beta distribution is defined by the parameters alpha and beta, and those themselves have come from some hyperprior distribution. Okay, are you guys still with me? Yeah.
Do we draw a new alpha and beta for each player?
No, we will keep the same alpha and beta, all right, to kind of say this is our prior distribution for all players, but you know, this player might have been drawn from the high side of that beta distribution. This player might have been drawn from the low side. Okay. Okay. So this is a lot of arrows and stuff, and so to kind of simplify this, let me see if I can fit this right here. There's something called a plate representation. Right, and so we can just say, and basically with the plate representation, you just write the names of the parameters. So you have alpha and beta, and you might say this goes into a beta distribution, and this will generate some theta sub p for used in a Bernoulli distribution. Okay, and we have a different theta p for each player. Okay, and from the Bernoulli, we generate our data y sub I. So this would be a plate representation, which is basically a simplified version representing this, okay? So A and alpha and beta go into a beta distribution. From the beta distribution, you're going to get this plate represents basically each player, okay? So you can imagine a box drawn around this theta and this set of y's, okay? And each of these is a different player, okay? So you put like a little subscript p in the corner to say each player gets its own theta sub p, and each of those theta sub p's generate y sub i's. Okay. And so if you read papers where they've done Bayesian statistics, you might see this plate representation diagram. Okay, something similar, and some of them get really complex. Okay. All right. Okay, so what are we going to do? All right. So now, okay, let's say we have a big matrix of data. Okay, of all the kind of hits and misses of, say 40 players. Okay, and we want to get estimates of all the unknown parameters. Okay, so there's going to be a total of 42 parameters to estimate. Okay, that is, we have 40 different theta values. We have 40 different theta values to estimate. Okay, and we also have alpha and beta of the beta distribution. Okay, so each player, like, we have to look at their strings of hits and misses to kind of get an estimate of what their theta should be. Okay, but all of those thetas that we've accumulated will also give us information about the beta distribution itself, for like what kind of theta values can be generated, right? So all of these kind of play a role into each other, right? So our joint distribution will have a total of 42 parameters. That's a lot of parameters in a joint distribution, right? The joint probability distribution for everybody parameters. Okay. So that would be, kind of our total posterior distribution of our data. Total posterior distribution of the parameters given the data. Will be something like this. Okay, we would have the probability distribution of theta 1, theta 2, up to theta 39 and theta 40, and alpha and beta. Okay, oops. Given our Y matrix. Okay, so this is the joint probability of all parameters given our data. Okay, and using Bayes' rule, this would be the likelihood probability of Y, okay, given theta 1, theta 2, theta 39, theta 40, alpha and beta, times the prior distribution of theta 1 up through theta 40, alpha and beta, divided by the thing, okay? And we're going to just ignore this, and we'll ignore the marginal, okay? And we'll say it's proportional to the, basically, I'm going to just keep this just the joint distribution of everything, okay? So if I multiply these together, that'll be proportional to the numerator, which is the joint distribution of everything, right? Joint distribution of okay, so let me just kind of factor that out. Okay, so we've got it's proportional to, I guess, yeah, I didn't need, so we've got y and theta 1 all the way up to theta 40, alpha and beta, okay? And we are going to factor this into the probability of, okay, we're going to look at just the first row of y, okay, so this is kind of the first row of y. This is player 1's data. Player 1's hits, okay? And so this is only conditional on one parameter, and what's that? Theta 1, okay? So if we isolate just this one row of the matrix, it only depends on theta 1's thing, right? Like whatever, it doesn't matter what the other people's thetas were, it doesn't matter what the alpha and beta were. Once we have that theta 1, this is the only thing that matters, right? So because it's a hierarchical distribution, figuring out the conditional probabilities in your data is a lot easier, okay? And we would continue this, and we would say this is multiplied by basically the second row of the data, which is conditional on theta 2, right? Okay, and so we would continue this, and we have factored this into until we get to the kind of the 40th row of our data. And this only depends on the 40th thing, okay? And I would need to also multiply this by the kind of the prior distribution. Okay, and so prior distribution of all the parameters is going to can also be factored, right? So the prior distribution, I guess, of all parameters, and there's 42 of them, okay? So we are going to say, so this itself can be, prior distribution of all the parameters can also be factored. Okay, and we're going to say the prior will be equal. So we can say theta 1 comes from, depends on alpha and beta. This is going to be a beta distribution, times the probability of theta 2, depending on alpha and beta, okay, all the way up to the probability of theta 40 coming from alpha and beta, okay. And now we need the prior distribution of alpha and beta, okay. Now this itself might have a prior probability distribution, But to keep things easy, we're going to just call this, we're going to say this is an uninformative prior, meaning that it is a constant value. Okay, so you know, whatever bounds this is, okay, as long as this is not uninformative over the interval negative infinity to infinity, okay, so alpha and beta actually have to be positive. So as long as it doesn't go from like 0 to infinity, you know, whatever numbers you want to use, even if it's like 0 to 1,000,000, okay, you can have an uninformative prior where it's just going to be flat, okay, and it's going to be some kind of constant, and then we don't have to worry about it, right? Because if I take this prior and I multiply it in here, you know, we're already saying this is proportional to something, okay, and so this is just some constant, okay? So it's an uninformative prior. It's going to be some kind of constant, okay? And if you want to do Gibbs sampling, all right, we would need a the conditional distribution of alpha based on everything else, and the conditional distribution of beta based on everything else, okay? And the math can be done, but it's a little bit messy. And so in this case, we can avoid it by doing the Metropolis algorithm, okay? So for all of this stuff where we have conditional distributions that are univariate, we'll use Gibbs sampling. And for this last step, where we couldn't figure out the conditional distribution, or maybe we just don't want to figure out the conditional distribution, we can use the Metropolis algorithm. Is that okay? So, so we're going to say the prior distribution of alpha and beta is flat and uninformative. And a constant, all right? I guess that's a little redundant, okay? To do Gibbs sampling, we would need to do math to find the conditional distribution of alpha and beta, okay? It can be done, but it's messy. Or it can be done, but it is a lot of work. I'll just say that. Okay, so to avoid this, we can use the Metropolis algorithm. Okay, so we're going to have a kind of a two-tiered strategy, right? So Gibbs sampling has reduced our super complex joint distribution of 42 parameters into a whole bunch of univariate ones, okay? There's like maybe like 80 univariate distributions, right? The univariate distributions of y given theta, this is actually, these are all Bernoulli's. Okay, this is Bernoulli, that's Bernoulli, and that's Bernoulli. Okay, and these are all betas, okay? So we have a whole bunch of univariate Bernoulli distributions and univariate beta distributions, and that's what Gibbs sampling will do. Okay, so we'll do this for Gibbs sampling, and then we'll do the Metropolis algorithm, right? All right, is this all right? Okay, so using what we have learned kind of about like conjugate priors and all of that, right? So for Gibbs sampling, we will update the conditional distributions of each player after seeing the data. All right, so we're going to say the posterior distribution of theta is going to be, for each player, theta sub j will depend on kind of the prior distributions of alpha, beta, and the data that showed up in the jth row of our data matrix. This comes from the beta distribution of alpha plus k sub j and beta plus n sub j minus k sub j, right? Where n sub j is basically the length of the row y sub j, okay, so total number of attempts. And k sub j is equal to the sum of the successes. Okay, how many hits the player got. Okay, and so we can do this, all right, so this can be done. Fairly easily, all right, and basically, we'll talk about alpha and beta next, okay? But you would do this repeatedly, okay? So you would get like many draws of this theta, okay? Using kind of the posterior distribution. And by drawing it many times, you can then kind of average those to get like an expected value for that player's theta, okay? So you get a posterior distribution, and then to estimate what the kind of the player's batting average is you would draw many draws of theta for that player and average them all together. And then you would do the same for theta 2, but you would do this one at a time. So you would do random draw for player 1, random draw of theta for player 2, random draw of theta for player 3, so on and so forth, okay? You'd cycle through all 40 values, draw your alpha and beta, okay? And then you go back to the top. Random draw of theta for player 1, random draw of theta for player 2, random draw of theta for player 3, go through all 42 values, and you just do this, thousands of times, okay? So you're gonna draw 42 values at each iteration. You do thousands of iterations. You're gonna have thousands of different random draws, and then you average them all together. All right, we'll stop here for today. I will be here on Wednesday. I will record my lecture. So if for whatever reason you don't show up on Wednesday, that's fine. But please do be sure you watch the video sometime over your break, okay? We'll see you guys maybe Wednesday, maybe next week. All right, if I don't see you Wednesday, have a happy Thanksgiving.